The vector is maximum when full speed is reached. Now that we know how the speed vector is produced, we next want to see how its components are obtained to complete the vector diagram. For this, there are two slotted racks, with the pin extending up through both slots. As the pin moves to form the speed vector, it also moves the racks to form the vector's components. To show this clearly, let's observe one rack at a time. Starting at 0 position, notice the rack movement as the pin moves into position to create the speed vector. The distance moved by the rack is equal to the range rate component along the line of sight. To show how this component is measured and is transmitted as range rate, return the rack to 0 position. Now watch this output. Output rotation measures the amount of rack movement, or component's length, and through the output shaft transmits the measurement as range rate to other parts of the computer. The other rack works the same way, but its movement is perpendicular to the line of sight. This component is bearing rate, and its value is transmitted through this output. When ownership's course is along the line of sight, the bearing rate component becomes 0. And the range rate component is equal to the speed vector. At 0 speed, both racks cross at the center, and the outputs are 0. This is a disk-type integrator, one of several different types. They can do many jobs. One of the simplest, the job in range keeping, will give you a pretty good idea of what an integrator can do. An elementary example of range keeping is one with stationary target and with ownership moving at constant speed along the line of sight. The problem starts with an observed initial range. At any moment, the sum of range change and initial range is present range. If ownership is moving toward the target, present range is obtained by subtracting range change from initial range. In this case, range change is a minus quantity. In the other case, a plus quantity. Present range, then, is the algebraic sum of initial range and range change. A disk integrator computes range change. So let's examine this part of the range-keeping problem. Starting again at the initial position and with range changing at a constant rate, say 10 yards a second, it's easy to see that after 10 seconds, range change is 100 yards. After 20 seconds, 200. After 30, 300, and so on. But what was the range change at all other points? With ordinary arithmetic, you couldn't keep pace with this problem. And of more significance, the solution would be in a series of jumps. Range doesn't change this way. The integrator computes range change like this. smoothly and continuously with the changing range. This example, with range changing at a constant rate, was used here because of its simplicity. Actually, in almost all situations, range change is not constant. Nevertheless, the integrator continuously computes range change and delivers it as an input to a differential. The other input is initial range. The differential delivers the algebraic sum as present range. Keeping the problem in mind, let's turn now to the mechanism itself. With the top raised, you see most of the basic parts: a roller, a disc, and a ball. There's another ball onto this one, and both are held in a carriage. These parts are shown here in schematic form to demonstrate operating principles. There are two inputs.